So we will continue. We will continue with this inseparable data sets. We will work with this example, make circles. As I told you before, we have this some functions in Python in sklearn.data sets. We can have some data sets. It's artificial data sets, in fact, which we can use for generating specific data sets, and use this one for testing models. So in this example here, we used to make circles before. It's a linearly inseparable data set as well. And the idea here is to try also to find a model for this is very complex problem, in fact. This one, it's a very complex data set. And we need to find, we have this red dots. The red dots, it's a +1, in fact, right? And the blue one, it's a 0. So also it's in the same, it's binary classification problem. And we have two classes here. And we have two features. We have x1 and x2. So we have two features, and we have two classes. It's a 0 and the +1, but it's linearly inseparable. And we need to classify it. So how can we do this? Is it possible to use logistic regression? Is it possible to use a perceptron, for example, for classifying this one? Yes, it should be possible. If we can work a little bit with the features. We have two features here. We have x1 and x2. So in fact, the data set, it looks like this one. So we have here x1, we have here x2, and this is y, or the label. For some points, it's a 0. For some other points, it's 1, 1, 1, and so on. So this is the data set, in fact. And it's complex. It's hard to find a decision boundary for this one, because it's if we try to plot a line, you can just imagine. So I will select a line like this one. So what will be the results now? Maybe below it, it should be red. So this one will be correct. This one will be wrong, misclassified, right? And when we go up above the line, maybe this one it's wrongly classified, right? And the blue one will be correctly classified. So what will happen now? The accuracy will be like maybe 50% or 25%. So it's impossible to classify this data set using a straight line, and we need to find something different. So we need to work with, we need to try to invent or construct a new feature which will help us to simplify this problem and make it linearly separable. So how can we do this? Okay, so I will work with x1 and x2, and I will try to test higher order features. We will try to test higher order features. So instead of working with x1 and x2, maybe we can work with x1 square and x2 square, right? In this case, I will try to use a perceptron, and the input to the perceptron will be, instead of using x1, I will use x1 square, and instead of using x2, I will use x2 square. So the output will be y. We have here is a bias. We have omega1 and omega2. So this problem, it's very simple. If we need to do the decision line here, it will be omega1 x1 square plus omega2 x2 square plus b equals 0. And if we can look into this equation, in fact, it's equation of, it's just equation. It's equation of circle, in fact. So if we set omega1 equal omega2 equal, for example, equal 1. So this equation will be x1 square plus x2 square equal minus b, or you can just say it's equal minus r square. Equation. So in fact, I just used this, logistic regression model or linear regression model. So I used a logistic regression model, and the input to the model will be x1 square and x2 square. So instead of using x1 and x2, I will use x1 square and x2 square. I will use the data set for fitting my model, for training my model, and after that I will use it for predicting, and I will print model coefficients. When we print model coefficient, we will get omega1 and omega2, in fact. So when we print coefficient, we will get omega1 and omega2, and if you can see it here, it's minus 8.17 minus 8.17, so equal 1 equal omega2. When omega1 equal omega2, it's exactly a circle, in fact. And when they are different, the shape of the circle will be different. Maybe it will be oval. And the intercept, in fact, when we print the intercept, we will get the value for B. So if we need to put it as an equation, it will be minus 8.17 times x1 squared plus x2 squared plus this number equals 0. So finally, the equation will be like this one. So in fact, it's equation with radius 0.9. So the radius here will be 0.91. This one will be R, and it will be exactly a circle. So when you simplify, I mean, when you try to use feature construction, when we try to construct a new feature, a super feature, which will help us to simplify the problem, I mean, the model, we just need a very simple model like this one. We just need a perceptron. You can try with this problem. In fact, I suggest you to try with this problem using MLB, for example. So in the break, you can try MLB here. MLB. You have two inputs, x1 and x2, right? And try to just select two hidden layers and with any number of units in each hidden layer and try to solve this problem using MLP.
I'm just wondering then, what's the point of using MLP when this problem is so easily solved through feature construction?
Yes, because some problems, it's easy to just visualize it and try to simplify it. I mean, this problem, it's easy to visualize it. But in real life, in fact, you will be working with large data sets and maybe it's impossible to visualize. So imagine that you are working with a problem and this problem, it's for banking, for credit scoring, for example. You want to get a loan from the bank and you want to apply. So the bank asks people to provide lots of features, lots of values, maybe 10, 20 values. Or I mean, I have a friend who is working in this domain, and he said those problems, it's really very complex. So maybe they have 100 features, and it's impossible to plot and visualize the data set. But you have lots of features, but I don't know which feature will play with. How can we use feature construction here? I don't know, because we cannot visualize the data. I mean, when we use this for this simple problem, it's just to understand I mean, how important those techniques. But the idea here is to use it in your complex problem from real life. If you are working for a bank, if you want to apply for a loan, for example, maybe you will provide features like age, income, maybe educations, maybe I mean, lots of information, in fact. So which one should be multiplied with the other? I don't know which. How can we manage this? So, but it's just to understand the idea behind feature construction. So, for example, in feature construction, we can try interactions. So I can try x1 times x2. It's a kind of interaction. I can try higher order features, x1 squared, x1 cubed, x1 to the power of 4. I can multiply x1 times x2 squared, for example. So you can try many things, right? You can try x1 times square root x2 plus 5x1. So those combinations, we should try very different combinations until we reach a super feature which will help us to build a simple model for our problem. So there are some algorithms, in fact, which help us. You can do it manually. So because it's in my table, it's in column. Each column is one feature. Maybe this is x1, this is x2, for example. So I can just try all different combinations, x1, x2, x1, x2 squared, for example. And I can use some statistical tool to find correlations. What is I mean, is there any improvement if I can use those interactions and those higher order features, for example? So from those statistical tools, you can understand if we can get a super feature which will help us to solve the problem. So the idea here, in fact, to try to generate a new feature which will carry more information and more knowledge from your data. So for example, for this problem, maybe x1 squared and the x2 squared, it's more useful than just using x1 and x2, right? Because x1 squared, it will carry more information, for example, variance and so on. So this is the idea behind it. So for example, we have a technique called select k-best, for example. So you can just select any number of features, and it's feature selection technique. And I can apply a feature selection technique. And this select k-best, for example, it can use Fisher score or chi-square score. So it will return a vector, and this vector will show you the score of each feature. You can sort them in descending order, and you can select, for example, the best 10, the best 5, and so on, because it's called select k-best. So if you have 20 features and I need to select the most important 5, you can just say, okay, I want to select best 5 features. You can define k equal 5, for example. So the idea here is to use your original features, x1 and x2, and you can generate different combinations of those features. As I told you, it could be x1 squared, x1 cubed, x1 times x2 squared, x1 times x2, and so on. And you can use select k-best to select the most powerful, for example, key features from those features, the original and the new features. So feature construction, it's very important because it will simplify problems, and instead of building very complex models, you can build a simple one. I mean, the simple one, it will be easy to understand. We have something in artificial intelligence. It's called explainable AI. Explainable AI. If I have this perceptron, it will be easy to explain because this is a decision boundary. This is a simple equation, and I know what does it mean. What does omega 1 mean and omega 2 and the bias. So I can just say that I build a simple model and it's explainable. But if you will go for this black box model, this one, for example, it's a black box model, right? This one, it's a black box model. It's hard to understand what does this one do, for example, what is the meaning of V1 and V2, especially when it become more complex. So when you have, for example, 1 million weights, because when you go for deep learning, for example, we can have a model with 5 million and 10 million weights, correct? So it will be impossible to understand anything. You just need to use it as it is. You just use it as it is, and you just, I mean, realize that it maps inputs into outputs. I mean, that is the whole task. But it will be impossible to understand. If you want to use this deep learning model in the hospital, for example, for medical diagnosis, because again, I can give my model X-ray images, for example, and it should make a diagnosis of a disease, for example, correct? It will be impossible to explain why this patient has a disease and why this patient does not have the disease. Maybe when you put the two X-ray images together, you cannot see any difference, but the model will make a decision, and it will be hard for people to understand why this one is positive, why this one is negative, right? So because the model is really complex and it's a black box model, but if you can simplify the model, maybe it will help people to understand. I mean, we call it explainable AI, in fact. So simplifying the model is very important for one reason, to understand how the model works, how the decision is making, and also for training. If number of weights is less, it will require less number of iterations. It will require less amount of data for training the model. Chances to overfit will be much less, right? So life will be much easier if we can do this. So so when you are working in your project, try to visualize as much as possible your data, and try to construct new features, because maybe those features will help you to simplify your model. And you can use some statistical tools. We have lots of tools, in fact, in Python. As one example, it's a tool called select k-best. It's called select k-best, for example. It will help you to select, a k powerful features from your data set. And you can use those k powerful features for training your model. So now, after training the model, we trained it, and we got this nice circle. Do you see this black circle? This black circle, in fact, we got it from the model. So the model, he understands that we need to classify the red, the blue as +1, and this brown dots as 0, for example, and it can generate this line, this nice line, this circle. So the decision boundary now, it's a circle, right? So yes. So do you have any questions for those inseparable data sets? When it's inseparable, I mean, you can just go for more complex model, or you can spend some time with data pre-processing, and you can try to find sober features which can help you to simplify your problem. You have also the code here. It's non-separable data sets make circles. You can just go for it and just try to run it. Try to invent. Try to select x cubed, x1 cubed, for example, or x1 times x1. You can try, in fact, try to use a tool which called select k-best, for example, to find the most important features for building your model. And also, I suggest also that in the break, for example, you can try MLP with this data set, right? We have, but just using X1 and X2. So try to choose MLP with 2 hidden layers, with 10 and 5, for example, in each 10 units and 5 units in each hidden layer, and try to train your model and try to find, get the confusion matrix and the accuracy, for example. So we can compare this simple linear regression model with MLP, right? Because we used as a trick here for feature construction, we will compare. Is it really possible to reach the same accuracy for this model? No, I'm sure that this model, it's more simple and it will be more accurate. When it's more simple, it will be more accurate and it will be more easy to understand. And even if you are building a system and if you should put this system, for example, in Raspberry Pi, for example, or portable device, for example, it will be easy really to do this if the model is more simple. But when it's more complex, I mean, everything will be more complex for deployment and production. Yes. So do you have any question for that part before talking about cross validation? We did also this cross validation before, but we need to revisit it one more time. This is the MNIST dataset. You can get MNIST dataset from Keras directly, and if you will get it from Keras, it will be already shuffled and divided into a training and testing, in fact. This dataset, in fact, MNIST dataset, it's 60,000 image for training and 10,000 for testing. So this one for testing and this one for training. You can upload it from sklearn, but in this case, you need to divide it, in fact. You need to split it, right? So if you will get it from sklearn, you need to split it by yourself, right? And if you will get it from Keras, it will be already, I mean, it will be just ready for use. In this model, I mean, I have enough data. In fact, I can use the test set for building my model, and the training set for training my model, and the test set we call it hold out. So this test set we call it hold out. I can use it for testing my model. So we can do this. So I used the SGD stochastic gradient descent classifier. It's a kind of feed-forward neural network, and I trained my model, and we have this kind of accuracy. We have this accuracy, precision, recall, right? And this is the confusion matrix. I mean, we did before confusion matrix for 2 classes. Now we can do it for 10 classes. I mean, in this problem, why? I mean, the classes we have from 0 to 9, so we can plot the true digits against the predicted digits, right? What does this one mean? It means we have 2,218 0 correctly classified as 0, 0 cases classified as 1, 6 classified as 2, for example, 5 classified as 4, 16 classified as 5, because there is big confusion, in fact, between 0 and 5, right? And also 11 classified as 6, because maybe 0, maybe 5, and 6, maybe they are close, right? Some people, maybe they just make it very close. And it's also with 8 as well. There is big confusion with 8, right? So, I mean, from this confusion matrix, you can find, I mean, what is the problem? So sometimes we have big confusion between 0, for example, and 8. Maybe it's smart to build a specific model to classify 0 and 8, a separate model. So we can do it like this one. For example, here, we have big confusion between 5. It's the same between 5 and 0. We have big confusion. We have big confusion also between 5 and 3, right? Because 5 and 3, maybe they looks similar, maybe. Also with 6, and also with 8, of course, right? 5 and 8, maybe it looks like the same. I mean, maybe people, when they write quickly, it will look like the same. So this is the confusion matrix for the test set, or the hold out set, right? We call it hold out validation, which means we divide the data into one set for training our model and one set for testing our model. And this is my classifier here. So we build the classifier. I just used all random values. You can check it online. and I just used X train and Y train for training my model. And after that, I used X test for testing my model. And the difference between Y predict and Y test, right? It would be used for calculating. Look, this is the difference between Y test and Y predict for calculating precision and recall. And I can get also this one for when it's macro and nano. I can get this value for each class, or I can get an average value for the whole model. So finally, the accuracy. I mean, I just used this model with default values, and the accuracy will be 90%. So this is the total accuracy. So I used here hold-out validation. Hold-out validation means we divide the data into one set for testing and one set for training. In case of cross validation, if you want to use cross validation, you need to define the model. So it's the same model which we used last time, SGD classifier, the same model, and we will run this model k times, in fact. So we need to select a cross validation factor here. It's a k. This one in k, in fact. So k equal 5. So in this case, we divide the whole data set into k folds, and we use k minus 1 for training, and one fold for testing was fold number k, for example, and we repeat this one k times. So should expect that we will run this model 5 times, and each time, in fact, we initialize the weights. Each time we start from a brand new model with new random weights. So when we use this cross validation score function, we will run this function, and each time it will give us the accuracy for each fold. So for k equal 1, we will have this accuracy. For k equal 1, we will get this one. For k equal 3, we will get this number. For k equal 4, we will get this number. And this number, it's the accuracy average. It's the accuracy for each model, in fact. So the accuracy for the model, which will be trained for k equal 2, 3, 4, and 5, and tested with k equal 1, right? And so on. So we will repeat this one 5 times. So each time we will get 5 accuracies, and the average accuracy, I mean the total accuracy will be the average. So if you need to find the accuracy, it will be just, we will take the average of those 5 values, right? So in fact, cross validation, we use it for performance check. We check the performance of the model. I will decide a model. We decided a model, right? And we need to use cross validation to check its accuracy, right? And once we had the accuracy, now I didn't divide, in fact, my data into training and testing. I mean, if you can see here, we use the whole X and the whole Y. So we used the whole data in cross validation. We divided it into k folds. We used the k minus 1 for training, and the testing was fold number k. We repeated this one k times. So each time we will get some accuracy. So the total accuracy of my model, it will be this. If I trained this model, so the minimum accuracy or the average accuracy will be this number. It will be 91%. So we are expecting that if you will train a model with this specification, you will get minimum this kind of accuracy, 91%. So
Wow.
after that, I will train my model with the whole data set.
300?
Yeah.
Mer eller mindre? Mer? 500?
Ja, har du
600?
spørsmål?
600? 1000? 1000? Under eller opp? 800? 700? 700?
Any questions?
900? What? Hæ? 2 ganger 2? 4?
Okay, so we will just continue because we will take a longer break at 12. So after running this cross validation, we will get the score from each cross validation. We will take k values. The average accuracy will be the average of those k values, right? And so we will get this score, average score from cross validation. This one will be the score of my model. And after that, I will train the model using the whole data set, in fact. So after doing this, you will start a brand new model with the same structure, and you will train it using X and Y, and you will test it, right? And this is the confusion matrix for the training, right? And this is the confusion matrix for the testing. And if you can see the accuracy here, it's almost 100% for the training, and it's maybe 92% for testing. So the accuracy will be this one. Of course, the accuracy here, it's higher than this one, because in fact, for each model of those, we used 80% of the data. So if we select k equal 5, what does this one mean? It means we will divide the data into k folds. We will train the model with k minus 1 and test with k. So in reality, we use 80% of the data for training each of those models and testing it with 20%. But for the, after doing this one and after getting this number, right, we will train a new model of the same structure with 100% of the data, with all X and Y. We don't need to have holdout anymore. And we will train the model using X and Y. And in this case, I tested its accuracy with a test set, or we should not have a test set, in fact. We should not have any test set. So I guess we have some problem here, in fact, because we should not test the model again with a test, because I don't have any test set. So maybe I did that with the whole data set, right? Maybe I did that with whole X and Y, or I don't know, in fact. But when we use cross validation, we should not have any test set, in fact, for testing our model, because it has been tested already. It has been tested already. So if you want to be, I have a recommendation, for example. So from the beginning, you can use 80% for training, and you keep 20% away for testing after cross validation. And you can use those 80% for cross validation. I can just use this one for cross validation. And after that, testing the model with those 20%. So, for example. Yes. So also in the break, we will have 1 hour break today. You can go also to this code and try to make some changes, and just to play with the code and try to make something. Different. So feature scaling and normalization. I mentioned that before. In fact, we have something called the data pre-processing and the feature engineering and the feature learning, for example. Data processing aims at making the raw data at hand more amenable to neural network, and it includes the data vectorization, value normalization, and handling missing values. Sometimes you have some missing values. So when you are getting your data, maybe you are getting your data from sensors or from a questionnaire, for example, from a bank, for example, and all customers has been asked to provide age and income and so on. So many people, they are missing some values, they forgot something, they don't have time. So when you will get your data, you will discover that you have lots of missing values. How can we deal with those missing values? The data set will be organized like this one. We have features, so we have some X1 and X2, for example, X3, and rows. Each row represents a data point or example, and each column will represent a feature. So if you have many missing values in one of those columns, one of those features, you can just ignore this one, just delete this one. If you have too much missing values in this one, so you need to check if you have too many missing values in one row column, you can just delete it, which will be very expensive. Maybe this one, it's age, right? So I don't need to use age because maybe 90% of the people, they didn't provide information about their age, for example. This one, it's a data example. This one, it's example. So maybe if you are missing X1 and the X3, you have only X2, maybe it's too much. You can just delete some of those examples with missing values. If you have very few values, for example, you can just replace those view values with maybe the mean value. You can get the mean value, you can get the median, right? Minimum value. So there are some statistical approaches for doing this to fill in the missing values. Value normalization. Normalization, it means we need to change the values into, I mean, we need to normalize all values between 0 and 1. And it's also important because if you are working with a problem from the bank, for example, one column is age. This age, maybe it's number between 20 and maybe 80 or 75, for example, right? So maybe income, the income will be from 1 million to 20 million per year, for example. So those numbers will be different. So if you want to make, if you can scale it between 0 and 1, it would be really very useful for your model, and also because of your activation function. If you use a sigmoid activation function, we will draw it like this one. This is my activation function. If you can see here, this is x-axis and this is y-axis. This kind of activation function, in fact, it squashes all input values into a number between 0 and 1, right? All large values from here, it will be converted into 1. So if we are talking about, for example, about income, so maybe the one who has 0.5 million per year, he will be converted into 1. Maybe the one who has 20 million per year, he will also be converted into 1, which means we are losing information. So if you have one column on your data and this column is about income, and the income, it's numbers between maybe 100,000 per year until 20 million per year. So maybe only very few cases it will be converted into a number between 0 and 1, and the majority of the other values will be converted into 1. So when we have all high numbers converted into 1 and all negative values converted into 0, it means we are losing information. In fact, we lose information because those values, we will just convert all those values into 1 and 0. So we will lose lots of information. So it's important to convert all values, all features into a number between 0 and 1. So we can keep variation in my data set. Because if I'm collecting information from students, for example, and I'm asking how many hours do you study per week, for example. So maybe one he say I'm studying 1 hour, someone else say I'm studying 20 hours, someone else is studying 100 hours, 120 hours. If I will use this squashing function, Gaussian function, maybe all people above 1 hour and a half or 2 hours, all those numbers will be converted into 1. So at some point, there will be no difference between who is studying 5 hours and who is studying 50 hours, because all those numbers will be converted into 1 for my model. So in fact, I spend the time collecting that data from people, but those information will be lost because I'm using this kind of activation function. Of course, we can turn around it by using, for example, a linear function. So the linear function will be like this one. So all positive values will be converted into the same values, and all negative values will be converted into the same values. Or maybe you can use ReLU, so rectified linear unit. So rectified linear unit, it will be like this one. All positive values will be the same, and all negative values will be converted into 0. Or maybe we can use something called the parametric ReLU, for example. So it's important to decide what activation function should we use, right? In deep learning, people don't care about data pre-processing, so they use, in fact, ReLU, for example. They use it a lot when you are working with images in deep learning, because the pixel value, it's a positive value. We don't have any negative pixel value. So the pixel value, it's usually a number between 0 and 255. So it's anyway, it's a positive value. So if we can use ReLU, it will be okay, because all those positive values will be mapped onto the same value. So if this one is x, this is y. So in fact, the ReLU, it will be like y equal x if x is greater than or equal 0, 0 otherwise. So this is ReLU. So the kind of activation function, in fact, we need to select from the data. I mean, I need to visualize my data. I need to look into it, what kind of numbers. If you are working with a problem which has some negative values, and if you will use a Gaussian, for example, or ReLU, in fact, in this case, you will destroy lots of information from your data set, because all those negative values will be squashed into 0 if I will use ReLU. All high positive value and all very low negative values will be converted into 0 and 1 also if I will use Gaussian function. So we need to decide. when we normalize, we will avoid this problem because I will be sure that all data points are converted to a value between 0 and 1, and all values will be represented. We will not lose any information, in fact, when we normalize. So normalization is very, very important. The place of feature engineering, this is the, if we can say that this is my pipeline, we have some data which are collected from different sensors, different locations. So I'm collecting my raw data here, and I need to build a machine learning model, correct? So I need to feed those data points into my model. I can just send them directly if I will use deep learning. So if you are building a deep learning model here, you can work, in fact, with the raw data as it is. But you need to be careful about what kind of activation function you will use here. But if you will go for shallow learning, it's like MLB, for example. In this case, we need to use feature engineering. We need to normalize. If I have X here, I need to normalize it, for example, before using it. Feature engineering, I mean normalizing. If I have some missing values, I need to fix it. It's very, very important. Otherwise, you will have some problem in your code because it will not accept missing values. I need to replace it with a number. It could be 0, it could be -1, right? So if I'm talking about age, about gender, for example, and just people provide 0 and 1, for example, maybe 0 it's male, 1 it's female. If we have missing value, in this case, we can just replace missing values with -1, for example. So when it's -1, the model will understand that it's missing, right? Because maybe it's missing its information, right? Maybe we have a customer who don't want to, reveal his gender, for example. So it could be something like this one. About income, people provide income. Someone, he will provide a number. Maybe some people don't prefer to, report their income, for example, and they just make it blank. In this case, you need to replace it with a number, right? Maybe when it's 0, it means he doesn't like to mention this. He doesn't like to, and it's information, in fact. When someone say, no, I don't want to mention it, it's information. Is this cluster of customers, they are the rich customers. Maybe those customers, they have some specifications. We need to understand them. So replacing those missing values is very, very important. So this is a place where we put, the feature engineering, where we clean and transform our data. Data vectorization, in fact, if you have some categorical features, we need to replace those with number, because machine learning cannot work with text. I cannot work with orange, apple, and banana, but I need to replace it with a number. Because, as you can see, now we go forward to calculating our class, for example. So I cannot work with text. I cannot multiply orange with a weight value, but I can multiply 1 with a weight value. So I need to select a number, a value for each categorical variable. If you will use one-hot encoding, because when we do it one-hot encoding, we will be sure that the output will be number between 0 and 1. When it's 0 and 1, in this case, we can work with probability, right? So if the output here it's 0.6, I can just round it to the nearest integer, so it will be 1. Or it means this orange belongs to orange cluster by 60% or 70%. So in fact, it's smart to use one-hot encoding. One-hot encoding, it means it will be, it will be 1 at orange and 0 otherwise. When it's apple, it will be 1. When it's apple, 0 otherwise. It will be 1 when it's banana and 0 otherwise. So in this case, if I want to build a model for predicting the price of fruits, for example, it will be just easy, right? It will be more easy when it's normalized the value, because at the end also, if I have this number 1, 2, 3, how we will deal with it if we need to normalize it, right? So it will be a problem. It will make problems later on. So it's a smart, in fact, to use one-hot encoding. Scaling and normalization, we did that before. You can also, in fact, go to MNIST dataset and try to when in MNIST dataset, it's a pixel value, and each pixel value, it's number between 0 and 255. And if you can remember, I divided it by 255. When we divide it by 255, it means we normalize it, in fact, to a number between 0 and 1. Because 0 divided by this number will be 0. 255 divided by 255 will be 1. So when we divide it by 255, In fact, we normalize it between 0 and 1. In standardization, in fact, we try to make all values have a mean value of 0 and a standard deviation of 1. How can we do this? By subtracting from each x its mean value, x mean, and dividing it by the variance. Yes, the square root of the variance, which is the standard deviation. In fact, we divide it by standard deviation, which is the square root of variance. So there are many ways for doing this. And for the feature construction, in fact, we started working with those feature construction in the last 2 examples. As I mentioned here, this is a sample which has an example which has x1, x2, x3 as inputs. We can try to generate new features from the original set of features. So for example, I can propose x1 times x2, x1 times x1, which is x1 squared. I can propose x1 times x2. I can propose x1 times x3. When it's multiplications, it means we consider interactions, right? You can also propose higher order features. I can say x1 squared, it's higher order anyway. For example, I can just continue adding x2 times x2, x3 times x3, and so on. So we can just propose many. And as I told you, we can use a method called select k-best. When we use this approach, we can select the most powerful features from my set. Yes, so we will stop here at slide 25. We will go back to it after at 1. And now we will take a long break, but in this break, please go back to the code in GitHub and try to run all those examples and try to make some changes. I mean, for example, use this function for, train test split, for example, and try to play with configuration of each multi-layer perceptron, for example, and try to see what will happen and what kind of difference. Especially for this make circle, for example, we solved it using logistic regression model. Try to solve it using MLP with different configurations, with 1 hidden layer, with 2 hidden layers, and so on. And then we will meet again at 1 or maybe before. So thank you very much.